Today we're going to start chapter 21, and we're going to go through sections 21, 21.1 to 21.6. We're going to learn how to name aldehydes and ketones, and then also some of the basic reactions that they undergo, and a review of how to make aldehydes and ketones. So the first thing we want to talk about is nomenclature. How do we name these things? So there's two different systems. There's the common system, and then there's the IUPAC system. So we're going to talk about aldehydes first. And in the IUPAC system, or the standardized system, if your aldehyde is in a chain, it's always going to be at the end of a chain. So you're going to find the longest chain with your aldehyde. Remember, we abbreviate aldehyde CHO. And you're going to change the E ending to a L. So hexanal would be 6-carbon chain with an aldehyde at the end. There's your hexanal. If your carbons, or if your aldehyde is coming off of a ring, you're going to name the ring and add the suffix carbaldehyde. Here's what that looks like. So for instance, if you have it coming off of a cyclohexane ring, this would be cyclohexane carbaldehyde. You don't need to tell me where the aldehyde is because you always assume that it's at the first carbon, on carbon C1, in the ring or in a chain. If, on the other hand, we look at the common way of naming things, you're going to take the parent name of the root and add the suffix aldehyde. This is for things like benzene. So benzene would be benzaldehyde. Or if we have the simplest one, the root of that is form, as in formic acid. This one is formaldehyde. That's the thing that preserves bodies and mammalian tissue for research. So that's formaldehyde. Acetaldehyde looks like this. So it's the acetyl group. That's acetaldehyde, etc. When you're looking at these, the carbon adjacent to the aldehyde is the alpha carbon. The next one is the beta carbon, and so on and so forth. Let's talk about naming ketones. So ketones can also be named using the IUPAC method or the common method. So using the standardized method, we're going to look at acyclic ketones first. So ones with chains. So you're going to look for the longest chain containing that carbonyl. And you're going to change the ending E to -one. That's why we have things like acetone. It's a carbonyl. You're always going to number the chain to give the carbonyl the lowest number. So something like this would be pentanone. And you need to indicate where that ketone is, so that would be on the second carbon, 2-pentanone. If you have a ring that your ketone is in, you're going to number beginning at the carbonyl carbon, but you're going to omit the number 1 from the name. So we're going to assume that carbonyl carbon is on carbon 1. So for instance, this would be cyclohexanone. If if I put a methyl group on here, we want to give that methyl group the smallest number possible. So since our carbonyl is on number 1, that would be 3-methyl cyclohexanone. If we look at common names for ketones, you want to name the alkyl group. There's 2 alkyl groups, one on each side. You're going to arrange them alphabetically. And add the word ketone. There's 3 common ketones that you should probably know. First one, the most famous, acetone, just has a methyl group on each side. The next one that's named commonly is this one here. This is acetophenone. And then if you have 2 benzene rings, this is called benzophenone. So a few other nomenclature rules. Is that if your acyl group is named as a substituent, you're going to take the IUPAC name or the parent name and add YL or OYL. So acyl group, substituent. You're going to take the parent and add YL or OYL. So, for instance, you could have the formal group, right? You can have the acetyl group. You can have the benzoyl group. Benzoyl is different than benzyl. So benzyl just means you have a benzene ring with the CH2 attached to your whatever you're doing it. Benzoyl group has a carbonyl. So those are not equivalent. Here's an example. This molecule is often called benzoyl chloride. So here's your benzoyl group attached to a chlorine. So those are common names. You're not going to have to be able to name things that way, but you do need to be able to recognize them. If your molecule has a double bond and an aldehyde, it's going to be named as an ene-al. And if you have a double bond and a ketone, then it's going to be named as an enone. So you're going to number your molecule to give the carbonyl the lower number. That one takes precedence. So that's the end of our naming. You should be aware of physical properties of aldehydes and ketones. And just the major physical property is that they have dipole-dipole interactions. So because you have that carbonyl that's partially negative at the oxygen and partially positive at the carbon, it's going to make your molecules polar. And so you can have dipole-dipole interactions with other polar things. So how do we make aldehydes and ketones? You have already learned a bunch of methods for making aldehydes and ketones, so I'm just going to remind you of them. So to prepare aldehydes, it depends on what your starting material is, which method you'd like to use. First one is if you have primary alcohols, you can oxidize those using PCC. Right, that's our mild oxidizing reagent that will only make aldehydes and not carboxylic acids. Second method is reduction. So that first one was oxidation. This is a reduction. So if you have an ester, you can reduce that with Dibol, diisobutyl aluminum hydride, and then water to give you an aldehyde. So that's our mild reducing agent. That's how we'll end up with just an aldehyde. You can also reduce acid chlorides using lithium aluminum hydride, but not the plain old lithium aluminum hydride. This is the fancy one that makes it less reactive. Oh, hold on. Okay, so there's our lithium reagent, and then again we have water to quench the reaction. You'll end up with an aldehyde at the end. So if you start with an ester, you use diisobutyl aluminum hydride, your mild reducing agent. If you start with an acid chloride, you use the large lithium reducing agent. Third thing you can do is hydroboration oxidation of alkynes. So if you use BH3 in THF and hydrogen peroxide with OH minus, you'll end up with aldehydes. So that's our first way, or those are our ways of making aldehydes. Let's talk about making ketones. So if we have ketones, we can get those by oxidizing secondary alcohols. And here we don't have to use the mild oxidizing agent. We could use PCC, but we don't have a chance of it going to a carboxylic acid. So we could use chromium trioxide or sodium dichromate or potassium dichromate. All of the chromium reagents here require sulfuric acid with them, and you'll end up with a ketone. Second option, so that was our oxidation option. Here's our reduction. So you can react acid chlorides. So again, here's our acid chlorides. Last option is hydration of an alkyne. So to get the aldehyde, you had to use hydroboration. To get the ketone, you just need water, sulfuric acid, and a mercury sulfate. So that's going to give us a ketone. You can get both aldehydes and ketones by doing oxidative cleavage. So remember oxidative cleavage of alkenes So if we have that case, if you do oxidative cleavage, so first step, ozone, second step, zinc and water, or dimethyl sulfide. Remember, you will cleave right here, and you will end up with ketone and aldehyde. So your starting material determines whether you end up with ketones or aldehydes. That's the end of this lecture. See you next time.